Section 4.3 continued to graph the other trig functions. Today, we're going to take a look at tangent and cotangent functions. On this diagram, you can see that the graph of the tangent function is not similar to the other functions we've looked at in previous sections. But we do have an asymptote like we do have with the cosecant and secant function, and it tells us that the graph is discontinuous at those areas. Also, the x-intercepts are of the form of x equals n pi. Its graph has no amplitude, and that means that it is no minimum or maximum values on the y values. As you can see, it continues in the positive direction and the negative direction with infinity. The graph is symmetric with respect to the origin, so the function is an odd function. The cotangent function looks like it's just the reverse of it, or the tangent function flipped. The graph is still discontinuous. It has asymptotes. Again, the x-intercepts are the form, but this one is x equals the quantity of 2n plus 1 pi over 2. Its period is pi. Its graph has no amplitude. Again, the y values, positive and negative, go to infinity, and it is also an odd function. The previous slides I will put on our resource page. This slide shows us the guidelines for sketching graphs of tangent and cotangent functions. To graph the function y equals tan bx or y cotan bx with b greater than 0, we need to determine the period, which is pi over b, not 2 pi over b, and the quarter points. Next, we need to determine a vertical asymptote using the following formulas, which is going to be y equals a tan bx, and bx equals a negative pi over 2, and bx equals pi over 2. For cotangent, it's going to be bx equals 0, and bx equals pi. After that, we need to determine the phase shift and the vertical shift. Then we need to determine the vertical stretch. Then we'll have the key points for the tangent function and the cotangent function. Here we have asymptote, and then it's going to be a negative 1, 0, 1, and then an asymptote. And for the cotangent, it's going to be asymptote 1, 0, negative 1. So you can see they are flipped. Just as it was in the sine function with 0, 1, 0, negative 1, 0, we have very common important points or key points with the tangent and cotangent function. After that, we're going to determine point location, multiply the key points by the vertical stretch, and then add the vertical shift. The guidelines for sketching the graphs I will put on our resource page. Let's start with our first example, y equals tan x. The first thing that we need to determine is the period. Our period with tangent and cotangent is going to be pi over b. For our other functions, we were using 2 pi over b. P is determined the same way. It is the constant by the interior function, which here it's x. Our constant is 1. So our period is going to be pi over 1, or just pi. Our quarter point is the same. We're going to take our period, and we're going to multiply by 1/4. Therefore, our quarter point is pi over 4. The next thing we need to determine is the location of the asymptotes. Recall from our previous slides, our formulas for the tangent asymptote is going to be bx equals a negative pi over 2, or solving for x, negative pi over 2b. And the other one would be bx equals pi over 2, solving for x would be pi over 2b. All we need to do is to substitute in, and b here is 1, so our asymptote is going to be a negative pi over 2, and our other one will be at pi over 2. Now all we need to do is to graph the function. Let's start by graphing our quarter points of pi over 4, 2 pi over 4, three pi over 4, and then 4 pi over 4, which is just pi. Then we go on the left side of the origin, which will give me a negative pi over 4, a negative 2 pi over 4, a negative 3 pi over 4, and 4 pi over 4, which is a negative pi. Let's graph our vertical asymptotes. Here, x equals a negative pi over 2. which would be a negative 2 pi over 4, which is a negative pi over 2, and also at pi over 2. Then recall our key points for tangent are a negative 1, 0, and 1. So we have our other quarter points graphed. There are 3 locations, so that will give us a negative 1, 0, and 1. Then I connect with a smooth curve similar to the one on the diagrams on previous slides. If I needed to create another vertical asymptote, I would just count from 2 pi over 4 another period, which would give us 3 pi over 4, 4 pi over 4, 5 pi over 4, and finally 6 pi over 4. And 6 pi over 4 would be 1 period away from 2 pi over 4. In other words, it would be pi units away. And then I would create another asymptote and again create the key points and graph my function. Let's verify our solution using a calculator. Here I've entered tangent x. I want to set my window. I do it in a similar fashion. X min is going to be my negative period, so it's a negative pi. My x max is my positive period of pi. My scale is a quarter point pi over 4. But since I don't have an amplitude, I'm going to make this negative 10 and 10 so I can see the whole range. Then I'll graph the function. It gives us the tangent function that we have centered at the origin. Then what I'm going to do is to calculate a value. And here I'm going to calculate pi over 4, and it should be a positive 1. You can test other values. Second, pi divided by 4, and I get 1. Therefore, my function is correct. Our next example, y equals 3 tan 2x. Let's start out by finding our amplitude. Here our amplitude is 3. Recall that with tangent, our values have to go negative 1, 0, 1. This just tells us that we're going to start at negative 3, 0, and 3. Now we continue with the period. With that, we know that that will be pi over b. And here our b is 2, so this will be pi over 2. We continue with our quarter point. We're just going to multiply our period by 1/4. So pi over 2 times 1/4 will give us pi over 8. Then what we have to do is find our asymptotes. And we know that our formulas are bx equals negative pi over 2 for tangent, which tells us that x equals a negative pi over 2b. And our other asymptote is bx equals pi over 2, solving for x. We know that this is going to give us pi over 2b. Substituting in for b, that will give us x equal to a negative pi over 2 times 2 is a negative pi fourths. And on the other one, x equals a positive pi fourths. Let's graph that information. Counting by our quarter point, which is pi over 8, is going to be 1 pi over 8, 2 pi over 8, 3 pi over 8, and 4 pi over 8, which gets me to my period, which is pi over 2. And then on the other side of the origin, negative pi over 8, negative 2 pi over 8, negative 3 pi over 8, and negative 4 pi over 8. We know our asymptotes are at a negative pi over 4, which is a negative 2 pi over 8, and a positive 2 pi over 8. Recall earlier we discussed that tangent is going to be the starting points of negative 1, 0, and 1, but with our amplitude at 3, we're going to start at a negative 3, 0, and then a positive 3 for our remaining 3 quarter points. So here a negative 3, 0, and a positive 3. Then we just complete with a smooth curve. We could count from 2 pi over 8, which is pi fourths, to another asymptote by going another period. So 3 pi over 8, 4 pi over 8, 5 pi over 8, and then 6 pi over 8. And that will be our other asymptote. Another way to look at it is I still have my 3/4 points in between to set my amplitude values, which would be a -3, 0, and a positive 3, and then completing with another smooth curve. Let's verify our solution using the calculator. Here I've entered the function. I set my window, which will be a x min of the negative period, x max the positive period. The scale is my quarter point, and I want to see a large maximum and minimum, so I set it -10. I graph the function, and then I just calculate a value. Here I'll try pi eighths, and I should get 3. Therefore, my graphing is correct. Our next example, y equals 2 minus 2 tan x. If I look just at the 2 tan x, I know that my starting points are going to be a -1, 0, 1, but with the 2, it would be a -2, 0, 2. But since this is negative, I'll flip this around, and therefore I'll start at 2, 0, and -2. It just flips my graph. Here, my period is going to be pi over b, and my b is 1, so it's just pi. My quarter point is pi times 1/4, which is pi over 4. My asymptote, as usual, bx equals a -pi over 2, or x equals a -pi over 2b. Substituting in for b, I get a -pi over 2. Similarly, with the other asymptote, I'm going to get pi over 2. All I need to do now is graph. I have my coordinate plane drawn. Of course, I use my quarter points to count all my marks on my graph. Let's do our asymptotes. They are going to be at pi over 2 and a -pi over 2. And of course, with tangent, I usually start at a -1, 0, and 1. But since this is negative, I'll start at the +1, 0, and -1. And then what I'll do is use the number 2 in front to graph that. So it's going to be a +2, 0, and then a -2. And then I'll complete with a smooth curve. But the graph of y equals -2 tan x is not the function I want. I want the function which is going to be 2 minus 2 tan x. Well, recall when I have a value that's added or subtracted from the function, I have to move it up or down. Here the 2 is positive. That means I need to move each one of my points up a value of 2. So here, since this is at 2, it goes to 4. Since this is at 0, it goes to 2. And since this is at -2, it goes to 0. And then I just complete that with a smooth curve. I'm going to verify my solution using the calculator. Here I already have it set in the y editor. I am going to calculate the value of pi over 4, and I should get 0. And I do, therefore my graph is correct. I'm going to verify using a calculator. I'm going to find the value of pi over 2, which I just found on the graph to be a -6. And I get the same value on the calculator, then therefore my graph is correct. One last example we'll walk through. Y equals a -4 minus 2 tan 1/2 x. Our usual order is a -1, 0, and 1. But since this is a -2, it flips and it goes from 2, 0 to -2. My period, inverting and multiplying, gives me 2 pi. My quarter point, multiplying by 1/4, gives me pi over 2. And when I solve for my asymptote, it gives me a -pi and a +pi. Coordinate plane, graphing my quarter points and marking my important points of 2, 0, and -2. But recall that my original function has a -4. So we just move everyone down 4. 1, 2, 3, 4. And for each one of these other functions, finally, this one at -2 ends up at a -6. Now, all I have to do is verify a point. I'm going to try pi over 2, and I should get a -6 on the graph, and I also get that on my calculator.